Okay, let's go back to the vertex cover problem. I hope you still remember the vertex cover problem from one of the previous lessons. So the input to this problem is a graph G, as you can see here, and the goal is to find a minimum size subset of the vertices such that this subset, all these vertices, together cover all the edges. And remember, as a possible application, we thought about, okay, so suppose you have a computer network and you want to monitor each of the links in this network, and to do so, to monitor a link, you have to install a little piece of software in one of the two nodes of the network, one of the two nodes of this link. Then you want to install this piece of software on a smallest number of computers, a smallest number of nodes in the network, in such a way that for every link, at least one of the two adjacent computers has this little piece of software installed. Okay, so this is the problem that we looked at, and we gave a two-approximation algorithm for it. Now let's make the problem a little bit more difficult and assume that each of the, so here, well, you see a solution. Let's make it a little bit more difficult by saying that each of the nodes, each of these computers, has a cost associated to it. Okay, a cost of, well, how difficult it is to install this piece of software on this particular machine. Okay, in the abstract terminology, this cost is usually called a weight, and so we get what is called the weighted vertex cover problem. So here, each vertex has a weight. So here you can see in yellow the weights for all the vertices. And now again, we want to compute a subset of the nodes, a cover, right? So that for every edge, at least one of the two nodes, at least one of the two endpoints is included in the cover. But now, instead of minimizing the number of vertices in the cover, we want to minimize the total weight of these vertices. So in this particular example, well, if you see this node here, it covers a lot of edges, but it's very expensive. Its weight is 17. So actually here it would be better not to put this very expensive node into the cover, but instead put these 4 other nodes into the cover. Okay, so this is the problem we're going to look at now, the weighted version of the vertex cover problem. So let's look back at the previous algorithm that we had for the unweighted version. Okay, how did it work? Well, it was quite simple. We first initialized our cover to the empty set, and the uncovered edges were simply initially all the edges were still uncovered. Then what we do is, well, as long as there are edges that are not yet covered, take an uncovered edge, okay, put both vertices into the cover, right? Remember, one vertex did not work, that did not give a good approximation ratio, so we put both vertices into the cover, and then, well, simply remove all the edges that are now covered by one of these two vertices from our set of uncovered edges. Check again if you have an uncovered edge, and so on. Okay, this was our algorithm for the unweighted vertex cover problem. So for unweighted vertex cover, it was a two approximation. And now the question is, would this also be a two approximation for the weighted version? Well, it's pretty easy to see that this is not the case. Even on a very simple example, a graph just consisting of a single edge, if the weights of one vertex, the weight of one vertex is much higher than the weight of the other, like in this example, then what will our algorithm do? Well, it will put both vertices into the cover. It will put both vertices into the cover. And then, in this case, the total weight is, well, here 101, whereas the optimal vertex cover would just have weight 1. So the algorithm that did give a nice two approximation algorithm for the unweighted version, for the weighted version, it's not a good approximation algorithm. So what we're going to do in the next lesson, we're going to see how we can use linear programming, and actually in a very special way, which is called linear programming relaxation, or LP relaxation. We're going to show how to use that to get a very nice approximation algorithm for the weighted version of vertex cover. So let's look at an approximation algorithm for weighted vertex cover. And what we're going to do is we're going to formulate weighted vertex cover as a linear program. And the hope would be, since we can solve linear programs quickly, that we can then get a nice, fast algorithm for weighted vertex cover. So formulating a problem like this as an LP always follows the following approach. Okay, so first we need to define certain decision variables. Okay, so for weighted vertex cover, or vertex cover in general, what we need to decide for each vertex, do we put it into the cover or not? So we're going to introduce a variable that represents this decision. So for each vertex v, I'm going to have a variable xv. And the idea is that the value of this variable being 1 corresponds to selecting the vertex into the cover. And the value of this variable being 0 corresponds to not putting this vertex into the cover. Okay, so now I have a decision variable, and if I could find the optimal values for these variables, hopefully that would correspond to getting an optimal subset of vertices, an optimal cover. So the next step now is, well, to formulate the condition that something is a cover using some constraints, and also to formulate the objective function, right, that we want to minimize the number of vertices, also as an objective function in our LP using the variables that we just introduced. Okay, so let's see how we can do that. So we want to formulate now the objective of our optimization problem and also the constraints as a linear program. So let's see how to do that. So we want to minimize the number of vertices in the cover, okay, subject to, what are the constraints? Well, it should be a cover. The set of vertices C should be a cover. So let's see how to do that. Let's first look at minimizing the total weight. Well, what's the total weight in the cover? Well, by definition, it's simply the sum over all vertices in the cover of the weight of that vertex. Okay. Now I want to introduce my decision variables by saying that, okay, the idea was, when is something in the cover? Well, that corresponds to putting the variable, giving that variable value 1, right? So we put v into the cover, that means that xv equals 1. So instead of taking the sum over the vertices in the cover, I'm now going to take the sum over all vertices and I take the sum of the weight of that vertex times the variable xv. Okay, and now indeed what we want to do, if we want to minimize the number of vertices in the cover, that means that we minimize this linear function of these variables xv. Okay, so we did the first step of our conversion to a linear program. We wrote the objective of our vertex cover problem as a linear function of our decision variables. So now let's look at the constraints. So what can we say? How can we formulate the fact that a subset C of vertices is a valid cover? How can we formulate that in terms of our decision variables? Well, it's a valid cover if for every for every edge uv, either u is in the cover or v, or both. Okay, well, we just saw that putting a vertex in the cover corresponds to setting its variable to 1. So we can rewrite this as the constraint is that for every edge uv, either xv is 1 or xu is 1. But hopefully you remember that this OR is not allowed in the constraint in a linear program. Okay, so we're not allowed to write this xu is 1 or xv is 1, but there's a very simple and nice solution. Instead of writing xv is 1 or xu is 1, we just write that xu plus xv is at least 1. Okay, and that means that that can only happen if one of the two is 1. Okay, so this is now our second constraint, and actually what you see here in this single line, you should think about as a number of constraints, right? For every possible edge, I have a constraint of the type, well, if the edge is uv, that xu plus xv is at least 1. Okay, so this is my linear program. And so just to make sure that you understand, let's look at a very simple example. Suppose I have this very simple graph of three vertices. So what does it mean? If I have 3 vertices, I have 3 variables. So let's try to write the LP for this particular graph. Okay, so here you see, well, I have a linear function of my variables xu plus xv plus xw. And the weights of the vertices, they now correspond to, well, these constants in front of my variables. The constraints are, well, for every edge, for instance this edge uv, I'm going to add a constraint that xu plus xv is at least 1. Okay, here I have 3 edges, so I would have 3 constraints of this type. So this is the linear program corresponding to this particular graph. Okay, so here you see the summary. We have these decision variables and we have this linear program. So there's a small problem, however, and that's, well, we said that these variables, if they're 1, it means we put them into the cover. If they're 0, it means we do not put them into the cover. So actually they only have a meaning when they're either 0 or 1. So that means that our linear program is maybe not quite complete. We should add some more constraints, which are called 0, 1 constraints, that tell us that for each variable, the value should be either 0 or 1. So the values come from the set 0, 1. Okay, so what does it mean? It would mean that we would have the following algorithm for solving our vertex cover problem. Okay, so we read the graph, then we generate this particular LP. Right? We introduce a variable for every vertex, and then we write, based on the weights of the vertices, we write our the function that we want to minimize, and then for each edge we write a constraint. We also put the constraint that each vertex has a value xv which is either 0 or 1, and then we would like to solve this LP, and our cover is all the vertices whose value is 1. Well, probably you already realized that this extra constraint, xv is 0 or xv is 1, is not allowed in an LP, right? Because this is an OR constraint. Well, what does it mean? It means that this is actually not just an LP, it's what is called a 0, 1 LP. In a normal LP, our variables can take on any values. Here, they have to be 0 or 1. So that's why it's a 0, 1 LP. And unfortunately, a 0, 1 LP is hard. A normal LP we can solve efficiently. A 0, 1 LP, well, that problem is NP hard, so the solution is not going to be efficient. So it seems that by formulating our problem as a 0, 1 LP, we did not gain anything. Well, that's not quite true. I mean, even though we know that a 0, 1 LP is slow, we can still, by a very nice trick that we'll see in the next lesson, we can still use this idea to come up with an approximation algorithm. So that's what we're going to do in the next lesson. Take the 0, 1 LP, modify it a little bit, and then, as we will see, we will be able to get an approximation algorithm.